So we're going to revisit that natural logarithmic function for a moment before we define natural exponential functions. So recall that f of x equals the natural log of x. If you look at this graph, you can see that it's 1 to 1, it's monotonic, all of those things, so it's going to have an inverse. So we can be sure that it has an inverse function, f inverse, and we know that the domain of f is from 0 to infinity. And we can see that the range is from negative infinity to infinity. So those would actually flop for f inverse. So the domain would be negative infinity to infinity, and the range would be from 0 to infinity. So the notation that we use to define the natural exponential function is this e to the x notation. The inverse function of the natural logarithmic function f of x equals the natural log of x is called the natural exponential function, is denoted by f inverse of x equals e to the x. So y equals e to the x if and only if x is equal to the natural log of y. Now if you take those points that we talked about before and you swap the x and the y's, you can see that this would be the natural log of x graph and this would be the e to the x graph. Now if you wanted to verify that these are inverses of each other, you could see that f of g of x in this case would be the natural log of e to the x, and using natural log rules I could bring that out front. So that'll be x natural log of e, and the natural log of e we know is 1. So this is x. And g of f of x would be e to the natural log of x, and this also happens to be x. So based on some of the rules that we'll talk about with the natural logs, that works as well. So they are inverses of each other, and these relationships come from those relationships. Now one of the most common ways that we use this is we solve an exponential function, or solve an exponential equation, I guess this should say, using logarithms. So if I wanted to solve 5 equals e to the x plus 2, I might start by taking the natural log of both sides. So I'd have the natural log of 5 equals the natural log of e to the x plus 2. Now this is handy because I know that the natural log of e raised to any power is just going to be the power. So this is going to end up being x plus 2. So I get that x is equal to the natural log of 5 minus 2. Now if you're asked for an exact answer, that's what you're looking for. This would round. It does have a value. It's about negative 0.391. But if you're asked for the exact value, that's the version of it that you want. Now for this one, I could start again by taking the natural log of both sides. So I would get that the natural log of 1/2 is equal to 3x. And if I divide by 3, I get that x is equal to 1/3 times the natural log of 1/2. Now be very careful. You can't multiply the 1/3 and the 1/2 or anything like that. You just have to leave it like that. And you could plug this in your calculator and round if you're asked to do so. Now you can solve for logarithmic equations as well. You could take e and raise it to both sides. So e to the natural log of 2x minus 3 power is equal to e to the 5th power. And we know e raised to a natural log is just equal to whatever's in those parentheses. So if I add 3, I get that 2x equals e to the 5th plus 3. And if I divide by 2, I get that x equals e to the 5th plus 3 divided by 2. And again, you could round that if you want to, but we're just going to leave it like that. Depends on what your instructions say. Now this one right here, I might start by writing this as x plus 5 to the 1/3 power, and then bring the 1/3 down. So I would have 1/3 natural log of x plus 5 equals 9, and then I would clear the 1/3 by multiplying by 3. So I get that the natural log of x plus 5 is equal to 27, and then I can take e and raise it to both sides, which gives me x plus 5 equals e to the 27th power, or x equals e to the 27th power minus 5. So that would be my answer there. Now, because exponents come from the inverse of logarithms, they have properties that go along with that. So remember, the log of a plus the log of b would be equal to the log of a times b. This is the exponential version of that. This is the exponential version of the quotient property of logarithms. And we could add here that, e raised to the a power raised to the b power would be e to the a times b. So if you wanted to add that one in, you can as well. And the domain of the graph of f of x equals e to the x, we said earlier that would be negative infinity to infinity. The range would be from 0 to infinity. This is continuous in 1 to 1 and increasing on its entire domain. It is a concave upward graph. The limit on the left as we go towards negative infinity is equal to 0. It does have a horizontal asymptote at y equals 0. And the limit as x approaches infinity of e to the x is going to be equal to infinity. So you can see all of the properties of the graph there.